Hello everyone, NNNI here, and today we'll be taking a look at a circuit made by Reid. He already explained a lot about this circuit in his video, which I'll link down in the description. He's got some great power electronic stuff on his channel, so please do check it out. So I was curious about this circuit, so I decided that I'd do it for myself and have a look at how it works. I'll get straight down to it. So this circuit basically consists of an oscillator which consists of 555 in this configuration, 47K, 3.3K and 100 picofarad resistor to produce 128 kilohertz square wave. I didn't have a 3.3K resistor handy, so I just used a 3. Something ohm. I don't the focus. I don't really remember the value, but it's an orange, white, red. So this is the 555 oscillator. This section is the frequency divider or the flip-flop, and this is the AND gate which controls the dead time. I'm going to be investigating the dead time circuit today mostly. So I turn on power, trigger the scope. Oops, it doesn't trigger on channel 2, I'm sorry. So this is the waveform you get out of the 555 timer. Let's turn on the frequency counter, channel 2. Anyways, the circuit runs at 154 kilohertz, even though the output frequency is supposed to be 62, which I'll tell you why later. So you just have a train of pulses with a very high duty cycle. It just goes low for a bit and the rest of it is high. And now this signal feeds into the flip-flop over here, and the output is on channel 1. So this is exactly what it does. Now this flip-flop is a CD4013BM, which is a dual D-type flip-flop. It's a D-type and an SR type independently. This is the truth table. As a clock pulse goes high, Q bar turns on. As a clock pulse goes low, well, it's complicated. That's why I got myself this sometime back, Forrest M. Nims Engineer's mini notebook, which is an excellent reference guide. I'll try to link it in the description. So it has some of these logic circuits in it. Well, at least it had. Yes. So this, the data or delay type flip-flop, is what we are looking at. So according to this thing, after the clock pulse arrives, which is as soon as the clock pulse goes high, when the data goes low, Q goes low and Q bar goes high, and the exact opposite when the data goes high. So it's something like an SR flip-flop without 2 inputs. So you just have a data pulse and 2 outputs. It's something like a toggle flip-flop. Very similar operation. Plus the focus. Yes. So it's very similar to a toggle flip-flop, and you can see that the output is the input divided by 2. So the output frequency is half of the input frequency, which is very clearly seen here. I'll just zoom in a bit. Okay, I can't. As soon as this thing goes low, the output goes low. When this thing goes low again, the output goes high, and so on. So you can see 2 complete periods here, from this falling edge to this falling edge, and from this falling edge to this falling edge has been turned into one complete period. And that's because a flip-flop doesn't need a continuous input to maintain its output. You just toggle it once, pulse it once, goes low, pulse it again, goes high, pulse it low, goes low, something like that. You don't need to keep its input low to keep the output low. So just divides the frequency. And you also have a Q bar output, which is currently on channel 3, and it looks like this. It's the exact opposite of channel 1. So this is how this thing works. And now for the most interesting part of this circuit, which is the dead time circuit. It consists of a 1K resistor and an 18 puff capacitor, which I didn't have. Anyways, the dead time doesn't depend on the RC value. I'll talk about that later. So now let me connect this dead time circuit. And you can already see the difference. Disconnected, connected, disconnected, connected. You can very clearly see that now there's a small gap on both ends of the pulse. They don't coincide with each other like they used to do, and this is very, very useful in these kind of switching supplies, half bridges, so that you don't have any overshoot, which is basically a short circuit through the two MOSFETs, and you have a lot of smoke and damage. And the dead time is almost the same as the low period of the 555, so the RC value has nothing to do with it. The clock pulse from the 555 feeds directly into the input of this dual AND gate. It's implemented through an AND gate, which is also mentioned here. The AND gate, the first logic gate that you'll ever see, maybe. So an AND gate's output is high only when both the inputs together are high. So I think something already makes sense. Since the output is AND gated, in order to have the output high, you need to have both inputs high. So on the AND gate in the circuit, one of the input is connected to the output of the output of the flip-flop, and the other input is connected to this delay circuit. So one input goes high and the other input slowly charges up and then goes high. So there's a small delay, as you can see here. And now I'll be probing the dead time thing on channel 1. Oh, oops, it's triggered on channel 1, so maybe I'll have to move that to channel 3. So you can very clearly see that there's somewhat of an RC slope over here, which creates the dead time. Okay, I think you get the point over here. So the dead time, maybe I even need to bring in another channel on this for you to understand properly. I'll do that on channel 2, which is going to probe the inverted output. So you can very clearly see this. Only when both the inputs are high, the clock pulse turns on. Not a very clear representation, but I think you get the point. Same thing with this discharge curve. So this RC thing adds somewhat of a delay between these two pulses. So that's the beauty of this circuit. I like it a lot. Very good design by Reid, as I've already mentioned. He has some great stuff on his channel. Do check it out. And I guess that's the end of this video. Thank you for watching. And oh, by the way, I forgot to mention, I got 100 subscribers and now my channel is eligible for a custom URL which I have to come up with. So maybe in another few days. Till then,